Hello, welcome to my presentation. I am Farhan Westgott. I am a PhD student back home at Lahore University of Management and Sciences at Lahore, Pakistan. I joined as a visiting researcher back in October 2018 under the supervision of Professor Lee Griffiths, Dr. Matt Ricci, and Dr. Ricardo Palama. The title of my talk is Practical Waveform Adaptation Scheme for FMCW radar that can be deployed on modern SDR hardware. I would start, quickly go through my research background and FMCW radars and USRP. Then I would talk about crosstalks and leakage in USRPs, followed by biostatic implementation, and will show a few of the results. And I would end with the synchronization and few of the proposed algorithms. I started working in the field of radar back in 2012. I have a US patent in the field of radar deception and jamming prevention. Most of my published papers were related to pulse-based radars, and in few of them I used embedded system solutions, so I never used a USRP before. Why FMCW radars? As all of you know, it has the ability to measure small ranges with high accuracy, ability to measure simultaneously the range and relative velocity. The signal processing is performed at a relatively low frequency range because of the beat frequency. It functions well in different weather types, compatibility with solid state transmitters and small weight and resistance to interference. So SDRs. An SDR, the concept is not new, but the rapidly evolving capabilities of DSP have made this SDR something to look at for in every field of signal processing. So SDR is a radio communication system where the components that have been traditionally implemented in a hardware, like the mixers, filters, amplifiers, detectors, so all of those things are instead implemented in the software. So a lot of mess has been incorporated in the software. So that has made the life very easy for designers, not only radar designers, but also especially in the field of communication. So when you implement this SDR technology into radar, so it becomes a software-defined radar. So it becomes a very versatile radar system. The NI-USRP are the Universal Software Radio Peripheral Devices. These are basically the SDRs that are manufactured by National Instruments. This is a block diagram of a USRP Rio, the one that I've been using over here. You can see that there are two different channels, and each channel has one receiver and one other port that can be either used as a transmitter or a receiver. So you have to keep this thing in mind. Apart from that, it has a very strong Kintex 7 FPGA board. So real-time signal processing can be incorporated in that FPGA. So it is a very nice device that can be used. I will quickly go through this paragraph so that you may know what the synopsis of my work was. So modern SDR systems are progressively pushing towards the use of adaptive RF front ends, and through the proliferation of accessible software-defined radar receiver hardware, it is now more than ever possible to develop complex radar system on a budget. So we cannot say that radar is a very costly device. It all depends on the application and the purpose for which the radar is being used. So there has been a wealth of research into what is theoretically possible in terms of waveform design and adaptation, but that has not been leveraged much for the FMCW radars. So we propose a project that aims to bring the practical and theoretical concepts closer together by developing practical waveform adaptation schemes for the FMCW radar that can be deployed on the modern SDR hardware. The work looked at either active FMCW radar waveform adaptation in the presence of interference or improving the detection performance of the FMCW radar by exploiting the flexibility in the chip waveform design, and try to improve the radar parameters that concern the detection of targets. So the applications, we were not confined to any particular application, but the applications that are most suitable for our work were mostly related to microdoppler, human detection, and if you prototype our system such that it can also be incorporated into ECCM applications. The device at the top is the USRP 2920. So the devices that I have used in my project are the USRP 2920, USRP 2922 and USRP 2943. In the USRP 2920 there is only a one channel. In the USRP 2943, this is the Rio device that I just showed you moments ago. So it has two different channels that you can see. So there is one, there are two ports over here and two ports over here, and both are different channels having a different oscillators. Okay, so there are a number of implementation issues that I faced over this period. I have just mentioned one of them, and that is this fetching error. When you implement something on the SDR or the USRP, so the speed or the data rate is dependent not only upon the USRP, it is also dependent upon the medium through which the USRP is connected. That can either be a PCI3 cable or can be an Ethernet connection. So and at the end of the day you have the host PC. So if you have a very good device, you have a very fast speed USRP Rio, and if your system is not good enough, you're not going to get good results. So you cannot change the parameters freely. You have to take into account all of those things while doing an experiment. Now coming to the crosstalks and leakage. So crosstalk is an unwanted signal between the communication channel, and it is a big a notorious issue in FMCW, because you don't get a breathing space like you do in pulse-based system, in which you transmit and then you listen for a brief period of time and then transmit again. You are transmitting something continuously. So the leakage is and also because of the inherent nature of frequency modulation, leakage has been a very disturbing issue for FMCW. Moreover, FMCW although have a good performance at short ranges, but if there is a leakage, you don't get that performance benefit. So these simulation that you're looking at your screen is basically the leakages, the transmit spectrograms and the corresponding leakages that you are observing on the receiver spectrogram. So different leakage issues were also seen using the spectrum analyzers, and the results were recorded, because we wanted to see if a USRP is good enough for an FMCW implementation or not. So this is basically a table that is showing, for example, if I talk about the case 1.1, it means that and this table is for the USRP 2943, which is the Rio one. If you transmit on the channel 1 and you're receiving on the channel 1, you can see that there is a minus 26 dBm of crosstalk, which is quite huge. It's not good enough. Similarly, if I transmit on the channel 1 and try to receive on the channel 2, then there is quite a considerable, like 40 dBm improvement in the crosstalk. So this is one good thing for those USRPs which have different channels. And similarly, a few simulations for different configurations at triangular and for a different carrier frequency. Excuse me. Okay. Now this table is for the USRP 2922. So these are two different USRPs. One is A and one is B. Two different devices, but having the same model, same characteristics and same specifications. So you can see that one of them has minus 18.4 dBm and other is minus 7. So you can clearly see, you can either say one of them is garbage, it's not working at all. So the point to notice that each device has its own crosstalk. Although you expect that not to cross a certain threshold, that looks quite a lot, but since it is an old device, you should keep in mind and first try to figure it out what the corresponding crosstalk is. Since these are old devices, there might be some issues inside the device. You have to see, and you can see that there is a huge difference between the crosstalks for the same model and two different devices. So what's the solution? It's better to implement FMCW radar if you want to implement those on USRPs, to implement those on with a biostatic configuration. So you can see that it's getting faded, and the corresponding crosstalks. And this is for the biostatic baseline distance of 5.5 and then 9 inches. You can see that it's getting faded away. And this table is showing the received power corresponding to different distances. So you can see that, and this is for the USRP 2922. So you can clearly say that around 6 inches, minus 80 dBm, I think it's good enough, which is very close to the noise power. And similarly, for configuration, if you place two USRP side by side, so around 11 inches it was like minus 80 dB, which is close to noise, and it's fine. So you can say that there has to be a certain distance for whatever type of device that you are using. There has to be you have to calibrate and check what is a suitable distance for the two devices in order to avoid the crosstalk. Okay, so as you just saw that bistatic is the right solution. So how to synchronize the two USRPs? So if I'm using USRP 2920, there comes a MIMO cable with that. You just have to simply connect the MIMO cable and two devices, get synchronized. So how to synchronize? Now at UCL I had a USRP 2943 and USRP 2920. So how to synchronize these two? For that we use a splitter. From the transmitter of 2920, the splitter, one of the port, it goes to transmitting channel, and the other goes to the receiving part of 2943. So you remember this part this is the same channel having the same oscillator, and this is the other channel with the same oscillator. So if this transmitting part of this goes to this, and you receive via the other receiving port, so you can do the de-chirping part by comparing these two. So it's a very naive solution. If you want to synchronize 2943 devices, so what to do for that? It's a costly device, octoclock. So you just have to connect the octoclock. You can synchronize up to 8 devices with that. Okay, now I'm going to show you 3 different algorithms which are quite doable, and let's see. Okay, so we have 2 USRP devices. Considering 2943 rear devices in this algorithm. So there's active transmission on USRP A channel X with some specification that I've named A, right? And there's a continuous reception by the same USRP at different channel. As you just saw that the different channel has a lesser crosstalk. And there's a continuous reception on a biostatic receiver at a safer distance on its channel Y, right? And we transmit the received average power that is being received by USRP A to USRP B, and the transmit received average power of USRP B to USRP A with its different channel. So it's kind of radar comm hybrid solution, taking into consideration the 2 different channels. So the power is being compared. And if the power of A is greater than power of B, the same loop keeps on repeating, nothing very difficult. Or if the power of A is greater than the power of B and it turns out to be wrong, the USRP A becomes a receiver and USRP B becomes a transmitter with a corresponding channel that I have named as X and Y channels with specification B, and USRP A has to convert into into a receiving mode with the specification B, not A. So the loop repeats itself with USRP A replaced with USRP B. So it's a very simple solution. Again, thanks to the flexible nature of the SDR that we can make use of. The second algorithm, there is active transmission on USRP-A. Again, the same setup. There's a continuous reception on USRP-A and there is continuous reception on USRP-B. Again, there is a radar comm solution from the other channel, it is transmitted, and there would not be a crosstalk between these two because one channel would be doing the radar part and another channel would be doing the comm part. Okay, the power would be compared. If power of A is greater than power of B, the same loop would repeat. Otherwise, there's active transmission on channel USRP-A with specification of B. So it's instead of switching off, the USRP-A would keep on transmitting with the specifications of USRP-B. So it's kind of beam forming can take place. So instead of, no device would remain idle at some time. So transmit beam forming by USRP-A and USRP-B, and the optimization of weights, as you know that in order to steer the beam, you have the corresponding weights. You optimize those weights. You have to. I'm in the process of formulating the weights for the transmit beam forming purposes, and then the targeted localized and the same process will be. So it's a very easy solution, but again thanks to the flexible nature of the SDRs. This is a very simple solution. One of the USRP-A, we only make use of that USRP as a transmitter, but do the transmit beam forming by the two different channels would require synchronization, but since having the same device, it's not that difficult. And USRP-B would do the receiver beam forming. If no target is detected for some time duration T, with corresponding switching operations can take place. Okay, so FMCW radar testbed has already, and apart from those algorithms, FMCW radar testbed has been now implemented in my setup. So you can just feed in whatever kind of waveform that you want to transmit, and you can see the corresponding response on the receiver side. So a testbed has been implemented and completed, and you can feed in your different kinds of waveforms. Like you have a number of waveforms, so you can feed those waveforms into the setup and see what you get, the beat frequencies, and also you can get the ring Doppler profile. I showed you this flow chart in my last talk. In which there were a number of black lines, so there's a number of green lines this time. So I started with the trends in FMCW radars, talked about USRP 2943. I had to learn LabVIEW and USRP, so I implemented that. I implemented conventional FMCW radar. I made a test bed, FMCW waveform design. Waveform has been made adaptive by a very simple solution that you saw. Bistatic FMCW has been implemented, synchronization is being done, and waveform has been, adaptive part has also been incorporated by again very simple solution. We have devised novel algorithms. We are in the process of implementing these parts, the practical waveform adaptation scheme and identification by the system using some. I would like machine learning to come into play for this part. And the thing that I intend to do in future is the real-time implementation of all those things. Instead of doing the DSP part offline, I can do all those things inside the FPGA. But it's a little more tricky and needs some time. So that's it. Objectives: to develop new waveform. The objective of all that talk and all the work that I've been doing over here, to develop new waveform strategies for FMCW radar systems, to propose new target detection techniques, to propose new adaptive techniques, to strengthen the research activities for FMCW radars, and the validation of the proposed algorithms and the proposed schemes via SDR implementation. So that's it. Thank you. Thank you very much. If you have any feedback or any suggestions,